All right, we're going to get started. Thank you for waiting. And our first presenter will be Aaron Blaisdell. He's going to tell us what he's been working on for the last 20 weeks or so. And he's going to talk for about 15, 20 minutes, and then he's going to invite us over to look at a demo of what he's created. I just want to let you know the presentations are about their entire project idea. The demonstrations may or may not include everything. So just know that there is more that they're going to be talking about than what you'll actually see here. But it'll be interesting. So let's give our attention to Aaron.
Good afternoon. I'm Aaron Blaisdell, like Andre introduced. I developed a self-leveling drone-assisted lifting device. As far as uses, a small version could be used to lift anything like, assisting like elderly folks in their laundry and things like that, all the way to ambulance EMTs with a larger version, using it to extract injured persons from like hiking and mountain biking and skiing injuries, and essentially it would be, so my research came from my curiosity about that very subject because a friend of mine who was an EMT for Berrytown had to respond a couple of years ago to an injury. A woman had fallen off of the fire warden tower at Spruce Mountain in Plainfield, and the extraction took about 7 hours to get her down out of there, and the hike is only about a quarter-mile hike. So by interviewing my friend and a couple of his coworkers, and by searching for how other municipalities do that type of extraction, I decided to try to develop this idea. So, requirements were that it needed to lift more than the weight, obviously, of the unit itself, and an additional payload. I wanted it to autonomously be able to come up to a certain desired hovering height and then maintain that hovering height. And then I also wanted it to be able to autonomously keep itself level, so that there wasn't, if it was used in an application like for an ambulance EMT, there wouldn't be chances of the patient falling off and getting re-injured. So, for the drone lifting device, I decided to use multiple drone motors and ESCs. ESCs are electronic speed controllers, and for the height, I'm using an ultrasonic sensor, and then for leveling, I'm using an accelerometer. So one of the EMTs would actually have to carry the controller, and it would be attached to the unit via an umbilical cord, and essentially would allow for the EMTs to just guide it as they bring the person out. Let's see here. So here's a system diagram that I developed. As you can see here, we have fans that would, create airflow, and so on one end we have an ultrasonic sensor that is set to maintain a certain hovering height, and then on the other end is the accelerometer that essentially controls this fan to keep the entire thing level, and then the controller would be something that one of the EMTs carries. So in my first test, I had just built a single housing with one motor and propeller, just to be able to test what kind of power it had. So as you can see, I just had my ultrasonic zip tied onto the frame, and we used a threaded rod from a rod holder in the center to hold different amounts of weight so that I could determine what I had for a payload based on the size of the motor. And had decided that I would need to create some guards, finger guards to keep, from injury, and then I wanted a gimbal mount for the ultrasonic sensor, so it attempted to keep the ultrasonic sensor always pointing straight down to get a good reading for the height. and we determined that for a single motor, we had about a ½ kilogram payload. I didn't really want to, I think I could have gone a little more than that, but I didn't want to for sake of possibly overheating the speed controllers. So I redesigned the prototype to a 2-motor system, and in my design, I implemented the guards that I planned on, and I also implemented a method of attaching multiple motors via PVC, 3/4 inch PVC pipe. In this first iteration, I had attempted to anchor it to the table where my controls were via a piece of wood. Unfortunately, that became too much for this motor to overcome as far as lifting it. So I had to redesign how it was anchored. And so my final design came out like this. And in this, we can see that I anchored it in the center via some plastic links, sort of chain links that I designed on SolidWorks with nylon bolts so that it would be less heavy and it would increase my payload. And then I designed a pseudo gimbal that just dangles freely, and it works okay, but it doesn't always point perfectly straight down, so that's something that I would have to redesign with more time. And then I had designed a control box to hold my batteries, the PCB board that I designed to hold the Arduino microcontroller that controls the system, and then the buttons for the EMTs to turn on the system and then command it to go to its hovering height. This is a schematic of my circuitry and the board design. As you can see, my board is here with the Arduino mounted in. I used ribbon cable to attach all of my connections to my ESCs and my sensors, and then I have compartments for 4 batteries so that I could, in the future, expand my system into a 4 propeller system so that I could lift more payload and then possibly do more research into how to expand the system, how to make it bigger, how to make it carry more of the payload, and then in turn eventually upgrade the battery system to be more practical. So here is a diagram of the basic PID control system. PID is proportional integral derivative controller, and so we have a set target height, and that comes in to the summing junction, and it goes between a proportional, an integral, and a derivative gains that all are brought together and brought into into my pulse width modulation, which is how I control the speed of the motors. And then that is sent out to the ESCs, which is the motor controller. And then my height sensor is my feedback to give me my error so that my gain system knows how to correct the error. And a similar system, this particular diagram is for my height sensor, but I have a similar system for the accelerometer that controls the speed of the other motor as well. So here's a couple little snips of my code. This is where I declare all my variables, so we can see that, I'm using, derivative and integral for angle and height. And then I have a proportional, integral, and derivative gains all for each motor that I have, as well as the 2 motors that I intend to add. And here is an actual snip of the PID code itself. So this one, takes and it implements the angle error for the blue motor and calculates the difference between the target and the actual angle, and then puts it through the controller equation to attempt to either slow down the motor or speed up the motor to bring it up or down level with the other motor, and then the other motor just relies on the height sensor to maintain the height, the set height that it was designed for. And that's it. Any questions?
How did you choose the size blade?
I took some information when I initially started out from a study from the University of Michigan based on the lift and blade size, the amount of blades, and blade pitch. So this study from the University of Michigan was just a rig that they had built to determine what kind of lift different types of propellers generate. And so I used the data from that study to determine that the kind of lift that I was looking for the scale of the project that I was doing was adequate to get the kind of lift that I was hoping for.
And you may have said it, this you say again, this is not the final solution for the body.
This is not, no. So this is just a two propeller system that I'll exhibit today that that when I turn on my system, the system will come up to the set height, which right now I just have it set for 55 centimeters, which is just barely above the rack that holds it. And the green motor will attempt to keep the system at 55 centimeters hovering, and then the blue motor will attempt to use the accelerometer to keep it level.
And then if you were to continue this project, you add a couple more, you get more controllers working, and you have to add more.
Correct. Yes, and I would have to implement a controlled gimbal, so a gimbal system that holds it, either an ultrasonic sensor or an infrared sensor. In the future, I would probably transition to an infrared sensor because, unfortunately, the ultrasonic is actually the slowest part of the software of my control system processing it. It's quite a delay to send the ultrasonic signal down and back up, whereas an infrared sensor would be much faster. And then if I had a controlled gimbal using motors to maintain as close to a perfect down position as possible, I think would smooth out my system as well. And then possibly implementing another accelerometer to attempt to level the other two motors.
Can you explain a little bit what the lack of a perfect gimbal, what error that produces or problems that causes the system?
Well, so when the system is racked too violently, what happens is the gimbal ends up acting like more like a pendulum instead of a plumb bob, and it starts going back and forth. And then so the ultrasonic is always sending a signal every 40 milliseconds or so, and if it's off slightly, all of a sudden you have a much larger error than you did prior, and it attempts to correct it. And sometimes when that corrects too quickly, the accelerometer has to try and correct the other end, and then all of a sudden you start getting wild oscillations. And we'll see that actually during my demonstration. So during my demonstration, I can exhibit to you that if I stabilize one end, so if I stabilize the green end with the height sensor, that the accelerometer end will stabilize itself. And I can exhibit to you that if I stabilize the accelerometer end, that the height sensor will stabilize itself. But when the two operate in tandem, there's a coupling error that I need to work out the mathematics for to essentially get rid of the oscillations, because it does start to oscillate pretty badly.
Anyone else have any questions?
Ian?
So if you were to take it to a particular you combine big enough motor that would
I think I would have to go to a larger propeller system, and there are motors that can drive that size propeller and give me the kind of lift I'd be looking for. Unfortunately, with current technology, the drawback is the battery system. So essentially, for that size system to actually carry a person, I think the batteries would be like a backpack that the EMT would have to carry, because unfortunately, because of the nature of the system, the amount of amperage that it draws, regular batteries, it would draw them down very quickly.
Anybody else? Come on over, and Aaron's going to demo this.
While he's doing that, Harrison, why don't you come over and set up?
So, right now I'm just hooking up my batteries. And so, first I'm going to just set it at a low speed that doesn't quite give it lift, and then it can gradually transition up to my automated system. So. If I stabilize the green end, you can see that the accelerometer on the blue end stabilizes itself. And likewise, if I stabilize the blue end, the height sensor tends to stabilize itself right below. But as you can see, I'm getting a lot of movement on the gimbal, and that gives me some funky readings. And so when I let go, we start to see wild oscillations. And so, as far as the software goes, it needs some more development to work out that system. So independently, both systems work exactly how they're meant to work, but unfortunately, something about the mechanical coupling of the system is some math I haven't worked out yet. And that's basically my system.
So, questions? Anybody? You've seen it?
There'll be time between the presentations at the end. You can ask Aaron other questions as well, and he can give you a private demo. There's a lot more. You can imagine there's a lot more. They're showing you just snippets of what they've done. And we're happy to see that it's working at some level. This is good.
So, Aaron, do you want to describe what the purpose of the green chain is?
Oh, so the green chain is just to keep the system anchored, so that it can have freedom of pitch, but it does not have freedom of roll. And then the pieces of conduit in the frame around it are to minimize yaw motion.
Yes, this is intended to control 2 degrees of freedom, and then the jig is to restrict the other degrees of freedom.
Okay.
All right.
I can't see anything in front of me.
Hello, everyone. My name is Harrison Fine. My project is a self-sustaining garden. So the problem statement: I am designing a gardening system that is self-sufficient, that waters itself and shades itself when it's needed. The system will control water to the garden in 3 different zones. The system will apply a percentage of 0.75 gallons of water when it's needed. That number was a number I chose. Through doing research, I found a number through the University of California and nowhere else. And I figured this was a good number to use for demonstrations purposes to see a good level of drop. The system will shade itself when the temperature is too high, and it will also follow the sun if the shade's not needed. It'll pivot to follow the sun to let sun into the garden, and when it gets too high, where the garden is going to lose moisture, or if it could potentially damage the plants, the shade will pivot to block the sun into the garden. So to do this, the system will continuously monitor temperature, sunlight, and moisture, or soil moisture. So the first system of this project is the watering system. I'm using just a water tank that's going to hold water. Ideally, it's going to hold water from collecting rain. So you have this outside of your house or outside of your barn, garage, collect water off your roof. And it has a three-way header splitter. It's just a garden splitter. So it separates it into 3 different zones. I'm monitoring the tank level using an ultrasonic sensor. And I'm using solenoid valves after the 3-way regulator to allow water to the separate zones. And the moisture sensors are what's giving me the input for the plants when it needs moisture, when it needs water, when it doesn't. The moisture sensors, it's the resistance type sensor. So these sensors come in the capacitance sensor or the resistance sensor. And that's just based off of the length and area of your sensor that you're putting into the soil. I'm using it to read the ADC value from the microcontroller, and I'm converting this into an equation that I can then use to determine the percentage of moisture that is in the soil in the different zones. To do this, this is the conversion I did, where technically the saturated water level is actually closer to like 1500, but when I tested it and I put the sensor into the soil, it would reach 1500, and then if you gave it like 5 minutes, it would settle out to somewhere around 2000 to 2200-ish, and that's what I figured would be a good zero. That's when it is 100% saturated. The water is all drained into the soil. It's not just water sitting on the sensor. The soil has absorbed it, and that is 100% soil moisture. To control the solenoids, I'm using transistors, the TIP122 NPN transistor. This, in my project, took the place of relays. I was going to use relays to control the solenoids, but instead I went to transistors because they're much more reliable and they operate much more efficiently. It needs a snubber in parallel with the valve because of the high back EMF. The microcontroller, it won't break anything. The microcontroller generously stops the code from running anymore to prevent any damage to any other components. The second system of this project is the shading system. For my shading, I am using 1 servo motor, 2 CDS cells, 4 shades, and a thermistor. The thermistor is obviously monitoring the temperature of the garden, determining whether or not shade is needed or shade is not needed. The CDS cells are pointed 45 degrees away from each other to track the sun's position. And the servo motor pivots these blinds to block or allow sun in. So it's essentially like a Venetian blind system. So throughout this process, I had several different ideas for the shading. The first being a system that pivots horizontally, and I used a worm gear system to try to operate that, and found that that was not the way to go. It needs to be much more stable, and it kept sliding up off of the driven gear. And it also only pivots there, so if the sun is somewhere over here, you're still going to get light into your garden. But also, this would only work if we were at the equator. So the sun is directly above us at its highest point of the day. So that idea doesn't happen. My next idea was to essentially do something like the solar panel systems, where it's a single vertical pivot, and it has a blind at 45 degrees. And so the CDS cells would track the sun, but it would pivot in an arc. The shade would be out about a foot away from the garden to try to cast as much of a shadow as possible. This still didn't work because after this point I determined that, or I found, that the garden needs to have a shade just completely open at all times in order to be able to block sun when it's needed or allow sun when it's needed. It can't pivot, can't track unless it's enormous and covering the entire thing at all points. So this is the final design that I came up with. It is still the Venetian blind system, and I'm using 50% shade, which is ideal for vegetables, mainly tomatoes. And these blinds here are mounted inside bearings, so that when the servo motor over here moves, it tips all of them. And they're all joined up here with a piece of metal that just allows them to pivot. So this just shows the method of how the shading works. So when the shading is not needed, so that it's going to track the sun's going to come in here, so this is the position the blinds are going to be in when the temperature is not high enough to warrant shading. So this is one point in the day, and this is later in the day, and you can see it's just going to track. That's the idea that I want. And so when the shade needs to block the sun, this is what I want. I want it to, whatever time the temperature gets to that point, I want it to start to block the sun. And it's going to keep tipping and tipping, and eventually the servo is going to have to kick back to block the other way. So it can't just keep going one way, it can't pivot 360 degrees. It has to kick the other way and start blocking the other way, which is what I'm trying to show you here. So it's going to start blocking this way, and it'll hit a point where it's like almost flat, and then the servo motor will have to kick the other way to block the sun from the other side. This is just a quick budget that I ran. In hardware, it's about $100. The servo motors were $20. That was for the one servo motor. The solenoids, that was for all the solenoids. And the moisture sensor was a pack of 5, and it was about $6. Questions? So I would like to have a closed loop control system, and that would be applied to the shading aspect and with the CDS to continuously track the sun and then move the solenoid as expected.
What about with the moisture? What would the control system use moisture sensor?
I didn't have a control system in place for the moisture sensor, but I can put one in place for a closed loop, so when the moisture gets to a certain percentage, it opens the valve. The only reason I didn't go that direction is because it would work better off of PWM. So if I had the valve operating off PWM to open more, shut more, to allow water to flow in different amounts. And it didn't really seem necessary. It still doesn't flow very quick. So you can still reach the desired moisture. The, yeah, so it's the ultrasonic sensor. The ultrasonic sensor watches the level in the tank, and based off of what the moisture sensor is reading, it's going to say you're at 40% humidity or moisture percentage on the soil, and we're going to try to get it up to 60%. So it just says, okay, we need 20%. We're going to take 20% of the 3/4 of a gallon, and we're going to convert that into a volume, which is obviously the gallons, converted into inches cubed, so we can get a height off of the ultrasonic sensor.
So it was actually doing taking the reading from a moisture sensor and then determining how much water it needs to have to get the right level on that.
It's supposed to. It's not currently working the way it should.
That is cool.
That is the goal.
So right now it's just doing 3/4 of a gallon. No matter what.
Right now, I'm having issues with the valves. So the valves aren't actually operating. I've taken the leads of my power supply and touched it to it, and they still don't open and close. They'll arc, but they won't open and close.
My usual question is, how the software, you design somewhere you have a fair amount of it, not all of it.
Correct.
Any other questions? We walk over and we show what we have learned. All right. So this is what I have going so far. I tried implementing the CDS cells to get it to track light, but the CDS cells give a very, bless you, thank you, a very bad response. It's very twitchy, and the solenoid valve would only go to the hard positions. It wouldn't go to any position in between. So right now I'm simulating sunlight using a potentiometer. So right now this would be like the sun is out, but it's not warm enough to implement the shade. So you're essentially looking at this like the sun is here and it's letting shade or sunlight into the garden. But if we warm up our thermistor, it's gonna freak out for a little bit because the temperature is coming up. Oh no! Oh no! So, because the temperature's coming up very slowly, it's dancing along that line, the threshold that I have set in code for it to start to transition over to blocking the sun. And because it's doing this so quickly, there it goes. So now it's warm enough to warrant having shade. You can see
guys are disconnected.
Yeah, it just kept going back and forth too quickly and broke the connection on there. But you can just see the servo motor. It's doing what it's got to do. Block the sun, kick over to the other position when it needs to. So that's that aspect of it. For watering, in my infinite wisdom, I decided to try to use a different container. This was what I was originally using, and it just didn't look professional. So I went with a new bucket, and things aren't quite sealed the way they should be. Some of the threads are a little short.
It's cooling down. It's cooling down.
And the motors were really cheap on Amazon when I got them, so I don't know if I might have burnt something up when I soldered the leads to them, or if maybe they just aren't making good contact. But right now, if I have it, so I'm pushing the push button, and that's how I check the zone, right? So I have 3 valves. Each would be going to their own separate zone. But for the purpose of this demonstration, I just had 3 right in a line that would go to the same bucket to drain. And I was going to have, off of push buttons, it would open or close the servo as it, or the solenoid for that zone, and it would check the moisture percentage of these little pots to determine how much water would need to go to that zone. Unfortunately, the pumps aren't working, or the valves aren't working, so I can't demonstrate that. But I do have everything in code that it's dancing the way that it needs to. It's just the motors aren't working, or the valves aren't working. Any questions?
The motor's like burnt out. You say you might have accidentally.
I'm not sure what's going on with the valves. I tested them and they worked before I put them into this, or mounted everything, and it could be potentially something not making good contact on the board now that I have it mounted up, or it could be that I soldered those leads and I might have fried it somehow.
When you first tested them, you test them all. Are they all like in series with each other, or did you test them each separate?
They're all separate.
Okay, they're all separate.
Yeah, they're not in a series.
So can you, is there any way you can demo the soil moisture sensor working? So can you show something on the screen? Or is it just one soil level?
I have right here. So right now I have 2 moisture sensors hooked up, and you can see right here in my global variables that they're different. So the one that's lower, moisture reading 2, is 1300. That's the one that has more moisture. That's got more water in it. That's this guy right here.
So if you take it out of there, can we see change?
Pour some
Pull
water.
the
You
sensor out?
should. Let's pull it
Have
out.
some water right there.
Well, that's the more saturated.
So you've taken out one of them.
Should we add water to
So-
the drier one and see the value change?
Yeah, let's do that. So moisture reading 2, it went up to 4,095, which is the highest point on the KL25Z for the ADC reading. So that's saying it's completely dry. It's not reading any moisture.
So if we dump some water in there,
Yep.
Value should go down. Was that 13?
That should be for moisture reading 1. Moisture reading 1 is now at 1758.
Yeah, it was like 2,300 before.
Yeah, so it's working the way it should. It's just unfortunately because the valves aren't functioning, we're not seeing the water flow. questions?
So as I mentioned earlier, sometimes these demos don't go as planned, but that's okay. The students have till the end of this week to re-demo, and Harrison has a chance here to show us how this all works together. So the students do make up little websites, and any future demo videos would be on that website.
I have another question. I
Yeah.
think maybe somebody already asked.
Go for it.
So when you're adding water to the bed, are those valves waiting for a certain amount of time to elapse, or is it based on the reading from the sensor?
So it's based off the reading of the sensor and the level from the ultrasonic. So the moisture sensor will determine what the percentage of moisture is for that zone. And then the valve to that corresponding zone will open until the height for the amount of water needed has been reached.
Gotcha.
So if it's, I don't know, let's say it's 1 inch for a half a gallon of water, it would wait until the 1 inch is dropped. And you would see that in the cystics value.
How does it trigger the watering? Is it like on a set time period? It says what's our moisture level, and then it waters, or does it wait for it to get to a certain level?
It waits for it to get to a certain level, below 40%. Below 40% soil moisture is when it's on a continuous loop. So it's continuously checking the soil moisture. And once the moisture is below 40%, the valve will open, supply it with the amount of water to get it to above 60%. Any other questions?
We're going to take a real short intermission, 5 minutes or so, grab some refreshments, and then we'll reconvene in about 5 minutes with the next group.
Hey, Harrison.
Here we go.
Okay, so you have to move them, okay. I was wondering how these were connected.
Yeah, if I had more time, I was going to try to make it. But this was the third step in Yep. That's what I was thinking. Have it set to 13.
Hi,
Hey, what's up?
how are you?
Good.
I'm Kelly. I'm the alumni relations
Oh, Kevin.
person.
We met very briefly.
Yes, we
The
did.
next time a while ago.
Yeah, okay. I thought so, but I couldn't, like, it's so hard. with
Yeah.
the minutes,
Yeah, lab coat.
yeah. Are you, like, putting this on the website of where the
Right
senior
now-
capstone brothers?
We're just streaming it on Zoom, and it's gonna go on the Yuja for profits. You know, I think Andre's gonna share it with people.
Okay.
I'm also recording it. I don't know. I think Andre has an ECET YouTube channel where he posts all the raw footage from the
Oh, okay.
presentations. So
Okay.
I'll probably go there.
Okay. I was just wondering, because I know, like Jimmy Marketing, like could use this stuff to, like, post
Yeah.
on. Yeah, so I didn't know if you, like, knew about it or if it was,
No, this is just in the department.
okay.
This is basically what they always do. So I don't know if they've ever even sent videos to marketing, but they record them every time.
Yeah, they
there's-
should, huh?
There's a whole archive of all the past.
Yeah, I feel like they should. It's pretty cool, like, to see these working. And
I think the reason they haven't, they've just been posting them on that YouTube channel is because it's kind of hard to get them up there through marketing. It takes a long time. And I think they want a nicer, more edited version.
oh, probably.
And we
Yeah.
just don't have the time to always do that. So we
Yeah.
just throw them up.
Just throw it.
You know, hands.
Oh, yeah.
So that people can just watch them. So, yeah.
And it, yeah, is that what, like, how do you get to that website? Is it, like, how do you get to the videos? Is it on Flickr or is it?
It just, Andre just shares them via email.
Oh, okay.
There are project websites that we just send out. I've been talking to, I've been talking with IT about working with marketing on a little bit more open way to upload stuff.
Yeah.
More official way, because I mean they're gonna keep posting whatever websites they can build.
Right.
So it'd be nice if they were a little more connected with the college.
Yeah.
But it's really difficult because marketing, have very specific standards for the quality of the content.
okay.
So we're trying to find some sort of medium
Gotcha.
where we can.
Oh yeah, because
maybe
like even
link
if you
them.
even if you post it like usually if I share anything with Jimmy, it's like through the Google Drive, like the Office.com thing, and that seems to really work because he uses like iPhone videos
Oh, really? Oh, okay.
for some like portions. Like if people can't, like meet in person, you can do like Zoom or even on your iPhone, you can like send him a recording and he'll put it in a video. So I feel like the quality like doesn't need to be that high.
I didn't know because I was basing this off of the lab website that
Okay.
they have.
Oh,
Have you seen that?
probably not.
They have like very, very nicely done curated videos interviewing project students.
Okay.
And they just go over like a more brief version of their
I think I've seen those like in the
presentation.
past.
Yeah, they're really
Okay.
nice.
Yeah.
But the problem is they don't have a lot of stuff to show current students and prospective students to really show them kind of the process. And like the more details about what you're going to learn and stuff. And so that's kind of what they're looking for is just like the student work directly.
Yeah,
that
instead
they
of
can
just like, oh,
talk
this is what
about.
I made.
Right.
Here it is. It's more
It's more like
like
a TV
how-
show version of
Yeah.
what they're doing instead of like the full-blown presentation. They like to have an example and specifically point out different things. And it's, direct student work instead of like a directed version of their presentation.
So marketing knows. I was just wondering
Yeah.
because I feel like sometimes like when I talk to Jimmy, I'll just be like, hey, I'm just forwarding this like to you just in case you didn't know, and he's like, no. Or sometimes he'll be like, no, I had no idea that was going on. Like he's like a lot of like faculty and staff kind of just like forget to tell us,
Yeah, I think that's kind of part of what's going on here too, but it's just, I think there's like hesitation to try to go through somebody else to get the stuff out there because they just want to share it and get it out to,
Yes,
the
yeah, they
public
don't want to wait
available.
for like Jimmy to edit it. And
But
then,
that's
like,
no reason not to tell them that it's where it is and how to get to it. You just tell them.
yeah, definitely. Because I feel like he could edit, like let's say that there's like a long video, he could still take edits.
Yeah,
Yeah.
absolutely. I could give them the raw files and everything.
I mean, I don't know if you like already, like talked to him about it or something.
No, I haven't talked to anybody in marketing at all. And I just barely borrowed this camera.
So the next two teams are going to demonstrate similar projects, but they approach them in different ways. And the general concept here is we've been thinking in our department for a while, it'd be nice to have something interesting for high school students to do or see when they come on tours. And so when you listen to their pitches and see what they're doing, imagine this or these machines operating with high school students, thinking about coming to college and seeing this kind of stuff happening. That's the premise behind this. Okay? So I will turn it over to these guys and they'll describe what they're doing.
So our project is called Feedback Battleship. And it's by me, Zoltan Bach, Tegan Bacon, and Ryan Mahoney.
So for our problem statement, we're tasked with building an autonomous system, hopefully one side of the game of Battleship. Like the professor said, it's mainly set up for high school students to come and check out what the projects we're doing as seniors. So our system has to launch the beanbags on the specific locations from the battleship board that we're going to have. It's going to be 7 feet by 7 feet. The locations are going to be determined by our code. The launcher also has to load and shoot multiple shots without human interaction. It's going to be able to calibrate it before the game plays to account for the varying board distances. So there's a 0 to 10 feet that's going to be separating the 2 game boards. The launcher's going to have safety systems so that no one gets hit, obviously, by the cannon or the beanbag. And the system has to fit into a 1.5 meter cube. And we're going to implement a tracking system. So that way, if you have any missed or overshooting beanbags, we can correct that and readjust.
So for the division of responsibilities, I was responsible for the shop power control, the pneumatic system, and the pressure analysis code, along with the safety system, and also worked on the game code.
I was in charge of making the hopper, the individual projectile loading system, the Pixie 2 tracking camera, and game code as well.
I was responsible for the backup system. I was responsible for the backup system as well as the rotary base. I also worked on target analysis code and game code. So this is the diagram of our overall system. The beanbag is initially loaded in the loader. The beanbag is initially loaded through our auto-loading mechanism, which was created by Ryan. The beanbag will go in vertical tube shown. It'll get pressed out of the loader and then go down into the barrel where Sully's air tank will fill with the required pressure for whatever distance we need to shoot. And then it will fire the piston, the press, the projectile being the beanbag onto the game board. And then the tracking camera can recognize the beanbags by the color and will tell us which space the beanbag landed in. And we'll know whether or not the beanbag landed in the spot that we aimed for. That's a feedback element in our target analysis.
So for my auto loading system, you can see here, I made it as like an additive hopper design. This allows me to print more features in case we want to have more shots. These are all 3D printed parts. You can just print another one and stack it, kind of like Legos. It features 2 12-volt linear actuators. There's a smaller one on the top here with a shorter stroke. This is meant for clamping the beanbags to prevent them from falling down. And then there's a longer 4-inch stroke actuator here. This is meant for pushing the bag out and down into the pipes where it can be loaded. There's also a limit switch here. This is implemented so when the bag comes down, it hits the switch, and then it tells the system that a bag has been loaded properly. If it doesn't hit the switch, then obviously there would be a jam, and then a human would have to come and unjam it. This is the electrical system I have for the system. It runs off a KL25Z microcontroller. It's powered by a 12-volt power supply, and then it goes into a dual motor controller here, and then it comes over to the clamping linear actuator and the pushing actuator.
So this is my rotor chase design. As you can see in the center, there is a shaft which drives the inside ring of the lazy Susan bearing, which is shown. The inside of the lazy Susan Lazy Susan bearing rotating the barrel to designated angles we need to fire at. The outside of the Lazy Susan bearing is mounted to the frame, so it remains stationary throughout. Underneath the bottom plate shown, there is a DC motor which drives the shaft, and the encoder acts as feedback, so the DC motor will turn in the direction of the designated angle, and will stop once the encoder reads that the angle currently is or matches a designated angle. The encoder converts physical rotation to a digital value between 0 and 2048, which 2048 is the resolution of the encoder, since there are 2048 revolutions or pulses per revolution. This is the electrical schematic. All of the components are shown to the right. I have a 12-volt supply going to my motor driver, and the motor driver drives the DC motor, which I explained in the slide previous. The pins from the Arduino, which is my microcontroller, to the motor driver act as outputs, and the pins going to the encoder act as inputs, because the encoder is pretty much telling the program where everything's at currently, and it checks to make sure it is where it needs to be. The DC motor is 16 RPMs and 70 kilogram centimeters in torque. 16 RPMs was relatively fast for the motor, so I implemented pulse width modulation, which slowed the motor down to the speed that I needed, which is 4.5 revolutions per minute. So that was 28% pulse width modulation roughly. The encoder is a multi-turn incremental encoder with a resolution of 2048, as I said.
So for the pneumatic system, it's designed as a PVC pipe as the barrel, and connected to that PVC pipe is a flexible hose which goes to the sprinkler valve. That goes over to an air tank where we can control the pressure using two solenoids. One of them is used to vent the atmosphere, and one of them is used to fill. The fill one is connected to a compressor or an air supply outside of it. We use the MBX 4250 pressure sensor to keep track of the pressure inside of the air tank and determine which solenoid needs to be open, whether there's too much pressure inside or there needs to be more. The sprinkler valve is a pretty simple valve. It uses a diaphragm, so it uses its own pressure to keep it closed. And then when the solenoid at the top left of the sprinkler valve is actuated, it releases the diaphragm very quickly, allowing all of the air to rush through. And this allows a large amount of air to flow through the system quickly. This goes back into the barrel, which I have a 3D printed piston inside of it. And that piston is connected to a spring using ropes on the inside. And that spring is used so that it slows down the piston at the end of its travel and then allows it to return back to the starting point. The pressure sensor is accurate to half a PSI, and the max range for it was supposed to be 36 PSI, but since it was absolute pressure, the actual pressure that we can use is only 22 PSI. For the safety system, it's an array of ultrasonic sensors. Each ultrasonic sensor has a cone coming out of it at 15 degrees, and this cone is in all directions. So in the bottom left, I made a mount that angles the ultrasonic sensors up by 7.5 degrees, so that the bottom of the emitted ultrasonic sensor is level with the ground. That way it doesn't interact with the game board or any of the bean bags on the game board. How it's designed is having 4 ultrasonics on each side, and each of these is reading out in that 15-degree cone if anything goes within that 15-degree cone, it'll sense it and send back a signal to the microcontroller saying that somebody has walked on the game board and it's not safe to fire. And until somebody's walked out of that range, it'll just stay at an unsafe level. And once they're out of the range, they can fire again.
So I was tasked with the Pixie 2 tracking camera. This is the camera we chose to track the beanbags, the positioning on the game board. This camera can track up to 7 different colors. For this case, we're using the color red as our beanbags. It utilizes software called Pixie-Mon, and you can utilize it in tandem with like a microcontroller. For this case, I used Arduino Uno. The purpose of this camera is to be used as a feedback to correct shot error in case the cannon missed the designated spot we were shooting. Then we can correct it using the camera software. Here's a quick glimpse of the software. In the top right here, this is the Pixie-Mon software. This is where you can track the objects and lock them in. You outline it in the box here, and then it will lock onto the color red. It will output the position data into the Arduino, and then you can use it further in your software to output like X and Y coordinates, so you know exactly where it's placed on the board. And then this is the setup. The camera is going to be mounted on a tripod here. And it has a 60-degree field of view, so we kind of have to push it out and angle it, so that way we can get the full 7-foot by 7-foot board in view. We have it laid out so the front row here is alphabetical A through G, and then the columns are 1 through 7.
So this is how the code for each of these systems works together. Once the system starts, the loading system code is going to run, pushing one of the beanbags down the barrel, and then the angle position code is going to run and determine what angle is needed based off of the position we're trying to launch the beanbag to. Once it's done that, it'll change the angle to that, and it'll go down to the pressure and safety code. It'll determine what pressure is needed to launch at that distance to hit the desired spot. And before firing, it'll run the safety code to make sure that nobody's standing on the game board. And once it does this, it'll fire the shot, and the tracking camera code is going to run and double check that where we actually hit on the game board is where we wanted it to go. And if it's not, it'll give feedback to both the pressure and the angle code, and so that we can adjust it later on. And after this, it'll go back to the system start and run it again.
So this is a flowchart of my code for the loading system. This is going to be the initial code that starts up when the system's powered on. It's going to come down, it's going to extend the upper actuator, which is going to pinch the beanbags in the upper system. It's then going to extend the lower actuator, the longer one, which is going to then push a beanbag down into the chamber and load it into the barrel. Now it's going to check the limit switch here. So if the beanbag does hit the switch, then it's going to retract the lower actuator and then retract the upper actuator that pinches the bags, so that everything will get shifted down. If the limit switch is not pressed, then it's going to wait for the user to clear the jam in the hopper, and then once it clears the jam, they can retract the actuators so that we can get ready for the next beanbag to be loaded.
So this is the flowchart for my rotary base. After the program starts, there's a homing process. One of the pins on the encoder is the index pin, which it sets off pretty much once out of the 2,048 pulses to establish where home is. So it'll rotate in the clockwise direction till it reads that pin, which then will implement the control system and saturate around that value and set home. Then it waits for angle to be input. If it happens to be at the correct position already, it will just ensure that the motors are off and then go back and wait again. But if the position isn't correct, it will check to see if the position is less than or greater than the desired position. If it's less, the motor will rotate the system in the negative direction until it reaches the correct position, then stopping the motors and waiting for new angular input, and vice versa. So if position is greater than desired position, it'll rotate in the positive direction until the angle is satisfied. So for my control system, the input is the angle value. The controller is my Arduino, and the plant is the motor. So the controller will read the input angle and activate the DC motor. And it will pretty much run until the encoder reads the correct value and stop it. If there is any overshoot, the encoder will still read that, and the motor will saturate around that value and settle close to it within 2 pulses. So these are a few snippets from my code. All the way to the left is the home code. So I implemented a different value for pulse width modulation. I did 10%, so the motors will activate in the clockwise direction at 10% RPM, and it will run until that index pin is triggered, then stopping the motors. The motor control code, which is in the center, as I said before, if the position is less than the desired position -2, because of the capabilities of the Arduino, it will rotate the motor in the negative direction and vice versa. I have the -2 and +2 in my code because the Arduino isn't capable of reading down to 2048 pulses per revolution. It's within 2 plus or minus, so that's roughly plus or minus 0.35 degrees, which in our system we can handle that with the spacing of the spaces. And then at the very bottom it says else both are low. That just means the motors are off if the angle is correct. And then all the way to the right, after the void loop, the next 4 lines are the code that reads the encoder. So pretty much when the code's running, it'll loop past that, constantly checking the encoder value. If you input a value, seen towards the bottom, it will read that, and desired position will be converted from the value of 2048 and 360 degrees. So what I ended up with was the input angle divided by 0.175 and so on, which will give you the position value closest to your angle.
So for the pressure code flowchart, the system's going to start and it's going to check the pressure sensor to see what voltage it's reading and convert that to usable pressure. And then there's 2 loops that are going to run. Either the pressure is going to be lower than desired or it's going to be higher than desired. If it's lower, then it's going to close the vent and then start filling air into the air tank. And if it's higher than desired, it's going to close the fill and open the vent. It's going to keep going through these loops until the pressure is within an acceptable range. And then at this point, it's going to close both of the solenoids, check the pressure again, and if the pressure is still within the pressure range, it'll go through the safety system. If it's not, it'll reset back to the beginning. in the safety system, it just reads the ultrasonic sensors and reads whether or not it's safety fire. And if it's not, it just keeps saying that loop until it is safety fire. And then it opens the sprinkler valve when it is. These are some examples from my pressure code. So it's constant, it's in a for loop, so it's constantly running. And up top is just an example of the pressure conversions that I'm doing for the MPX 4250. And below that, I just have the code that I'm running for filling the solenoid, and then below that is for draining the solenoid. Each of these is just running based off of whether it's reading below the desired pressure or above it. So for my control system, the input is the desired pressure that it needs, and that'll go to the microcontroller, which controls both of the solenoids, and the output is going to be the pressure in the tank that it's actually reading. The pressure sensor is going to give the feedback to the microcontroller, which will tell the microcontroller which solenoid needs to be open and which one needs to be closed.
So this is our budget slide. These are just some of the items that we used. For example, my encoder was $24. The wood seen in the frame was $25. The 3-inch by 10-foot PVC conduit was $82. We spent roughly $480 total.
So this is our Gantt chart, which you can't really read in this slide, but this is overall what we did throughout the semester. I'll zoom in on different parts here. So at the beginning here, we were working on the first subsystems, and we were all ordering parts for it, doing testing, and then building that subsystem in those roughly 3 weeks. After that, we were working on our second subsystems. So this was the pressure subsystem, rotary base, and designing PIXI 2. We were all, again, ordering parts, testing, and then working on code throughout this whole thing. And then finally, we were mostly working on implementing the systems together and just combining everything so that we could have some final testing.
Questions? Dan?
So you said for startup it turns clockwise if I'm in position?
I believe, yeah.
So what if it's already past that position?
If it's past it, it'll take a full revolution.
Is that not a worry with any wires or hoses?
How I have it set up right now, it could do it with barrel on, but the wood is too wide, so there's only, hits the wood if it rotates too much, so only it's best done with barrel on in some positions. Yeah, yeah. Yeah. I can demonstrate homing and my control system, which I plan to show first, and then after that, I'm just going to do designated angles for firing.
It's not all together.
Not all of them, but no.
Give me a second, Ryan. I think what I was asking, you can't use the same feedback right here.
Yeah, that's correct. In order for the feedback to fit for each barrel, we have to have 3 strips of tape onto the feedback, so that way the diameter is stretched down, so that way it can fit into the solid system.
Yeah, it's just also going to add, that allowed us to get the same weight in between feedbacks by having tape to them.
I think at some point, one of both of you may have mentioned that it sounded like the lower pushes feedback. That's not the case. You would actually slide to show the top. So in the longer, you actually pushes that beam back out. It actually twists and falls.
Right. It's kind of, it's angled here, and then gravity takes over, and then as it comes down, it slides out, and then it falls into, and then it slides down there. No. Unfortunately, it's kind of hard to make the bean bags in SolidWorks. That was the closest thing I could represent with the dimensions.
More like so.
Yeah.
Yeah. Any other questions?
Time to get hit by a beanbag. Let's go.
All right. All right. So you want to take this off so you can. Okay.
Wait, fire is off.
Why are you taking it off the base?
Tegan wanted to demonstrate his base.
Was that what you're talking?
First, yeah, to show the control system.
I want to show you how much is a bench press.
Let's get to it again.
So, if everybody wants to come closer, this is just kind of this rotating for now. So, 0 isn't, it's off center slightly. So, say this is the 0 position of the rotating surface. It'll rotate in this direction until it reads 0 on the encoder, which is here roughly, and then we'll saturate around that value. So once I upload it, I'll rotate 10% pulse width modulation until it reads saturates and then ohms. So now that 0 is the value, I can use serial monitor in your Arduino software, and you can see the position readout is constantly updating. So we're at -1, which is 0.18 degrees off from where 0 is. So if I put an angle in, which was 30 degrees, what was off, but it saturated around that value. Now, the motor driver I'm using, you can manually override and force the motor to go in a certain direction. So if I go this far, it will go back to the value, saturate until it reaches. So that's the control system. Still moving around.
Local hopper to the top. This is what's going to do with beanbags and the tables that live inside the barrel. So I'm going to push the button now, which is going to clamp the top, and then it's going to push the longer actuator out, which is then going to push the lower beam bag out and load it in. Then it's going to reset.
So if you push the button again, it would stop the beam bag again?
Yeah.
That's good. So I have my code running, which right now I have it manually closed off, and this solenoid is gonna open up, and then the tank's gonna fill up with air, and it's gonna, the pressure sensor is gonna constantly read it. Once it's at the desired pressure, then it's gonna close off the solenoid and then fire the beam back.
Are you using the safety system at all
I'm
now?
not.
And
So nobody's standing in the gate.
approximately where is it going to land?
It should land in
In the square somewhere? Okay.
Yeah.
And cover our ears?
Yeah.
It'll be loud.
So is this all running under software control now?
Supposed to be. I don't think that's working. It's not reading the right value, so yeah, I can't fire it.
Just force it.
Pressure sensors on the right value.
What would you estimate it is? You gotta-
Way too high.
Okay, just manually set it, and then force it.
No, I have to drain pressure, else this thing will launch.
It's like a screaming goose.
So it's around the right pressure now, but
Yeah, just comment out the loading part of the straight from water.
no, I don't have to pull for it to just go straight to fire.
It's good to accurate the automated pressurization scheme.
The pressure sensor. Is it the sensor? Is the sensors on? So deciding the sensors.
Yeah, it's not fun.
So like,
That's what I was.
Are those sensors
Just
on?
take your controller.
You're all
Something
else
out,
and-
every download.
no, it's not.
It's reading negative five, which is not supposed to be. So just, yeah, so it's not gonna work.
Okay, so just right in here, wherever your distance are. This is just coming up this way. Yeah, you download that.
That's, there's some. This is.
Get closer to the closet. It only needs a push on the top. Okay, okay.
Okay.
Well, we got one test fire out of it.
Yep.
Give us a heads up if it's
It's supposed to fire right when I click this, so. And it does nothing. Okay. Well,
Did do it? All right. You'll have to check out the video on their website.
It has launched it many times.
Yeah.
yep.
We've all, those of us in the class have seen it launch many a beanbag.
Yeah, yeah. All right. Were you going to show anything else?
Yeah, I'm gonna try wiring this up and show this.
Okay.
This is the nature of prototypes. They're finicky.
They're finicky, and there's a lot of interrelated circuitry here. Doesn't take much to follow that.
As long as it doesn't split open through Zoom.
It's not shooting, so you can show off.
Alright. So, I'm gonna attempt to demo all the beanbags lovingly. So, every time you hit a button, it's supposed to cycle one. So it's gonna clamp, and then it's gonna push the bottom one in. That one got caught. Where's the limit switch? You both that? Apparently not on there. No.
Stick my hand with it. You got pressurized system. That's fine, if you can use one more. So that seems to be working. So did you calculate how high a stack you can legitimately do, like 5 or 6, 10?
With like the weight.
Yeah, weight-wise.
I believe Tegan's gearbox can only hold, what?
I calculated 30 pounds total, so that's on top of the weight of the barrel.
You gotta be able
So I think you have like 4 or 5 more pounds to play with.
to, okay. They're only 100 grams each. So.
Yeah, the beanbags are like 130 grams a piece. Then the 3D printed parts are just plastic, so they don't weigh much.
Okay. Any more? Yeah.
Yeah, so that's reading great. So the safety system right now, when I hold the push button down, it's simulating it checking whether something's in the way of the game board. And on the code, I have all the different distances of the ultrasonic sensor, which are updating based off of what it's reading. So if somebody walked through the display game board, it should update.
So is that shown on the screen? Or?
Yeah, it's showing it. They're highlighted yellow.
So if I walk through here, something will happen?
It should update on the screen.
So should I?
You can walk through.
Is there an LED or something that will come on, or?
You should just change the distance readings on this.
So did something happen, Ryan?
Yeah.
And it should change the safe fire principle as well. Yeah. Now it should be safe to fire, because nobody's going to wear the game board, but once he walks through, it should change the safe fire variable.
So do it again? Continuously running? Where is the safe fire variable on here?
It's up on the top there.
So what is, one is not safe,
Yeah.
and then what's safe? There it is, yeah. Yep.
So do you guys have a video of you firing this thing? Nobody asked you to take something last.
I don't.
Yeah.
Okay.
All those test shots, no videos? Took a
Okay.
video? There were lots of test shots.
Yeah. All right. Well, it looks good. Thank you.
Yep.
So we're going to listen to the other team talk about their approach to solving the same problem. And they'll give us a demo.
Like not like this, like this.
You want like this?
Well, good afternoon. Thanks for coming. My name is Wesley Brown. This is my associate and partner,
Wait, Gordon.
Wade Gordon. Our project was, again, as we've already talked about, kind of the other half, the other side of the coin of the team that's just presented to you. The premise is for us to create one half of an autonomous game, which we'll play like the board game Battleship. And we're going to use electromechanical systems and software to do that. The games will eventually, the idea is that they'll play each other. Now, the system will play the game by, again, as we've already discussed, it'll launch beanbags onto a game board, a physical game board, and use a camera to see where they landed. And then, of course, correct later using that data with the camera.
So the requirement and goals of our project was originally a 10-foot square that had all of the original placements, squares. So the targeted coordinates determined by our feedback systems and our controls. And it must have a capacity of 20 beanbags or so to continuously play the game. And it must calibrate for any sort of variation in board lengths between boards. So the idea of the system is to use a spring-powered cannon to launch our beanbags. They're using a motor to pull back a spring. Before the spring gets compressed, a few things need to happen. The cannon has to be automatically loaded. In this state, the cannon will move vertically. After being loaded, the system will start running the gameplay algorithm, which we'll get to in the next slide. This will determine the angular position horizontally and vertically. We have sensors on both axes to determine position. The horizontal position will be gear-driven by a DC motor. This system utilizes the properties of an incremental encoder. The reference, as I said earlier, is determined by the gameplay algorithm. The vertical position system is driven by a linear actuator. The linear actuator possesses a sensor to track a position, which is necessary for the control system. So, assuming everything went well, when it's planned, the beanbag will be launched at a specified position on the board, which will be detected by the Pixie 2 camera, which recognizes colors and objects. Now, I'll give it off to Wes to talk about the gameplay algorithm.
Okay, so the basic idea that we thought up to develop our software that plays the game is it's going to have two major modes. So at any given time, the software will be either searching, scanning mode, which will just follow a predetermined sequence of space coordinates that we've punched in. And it'll just scroll through those and shoot at each of those coordinates, and it'll just follow that list, basically. Now, once it gets a hit, it'll change to a different mode, which we call search and destroy, where it'll start kind of scanning around the space that it purported to hit at until it finds the orientation of the ship, whether it's horizontal or vertical, and then following that line until it's destroyed the ship, at which point it will return back to the scanning mode, and it'll just keep looking for more ships. So now we're going to go through and talk about the different subsystems, the different sections of the project that we worked on throughout the semester. So the first one up is the launcher and the trigger mechanism. So here's just a little diagram to give you a better idea of how this system works. You can see we have two springs here, which are being pulled back with a DC motor, which is attached by this piece of cordage here. And we have two very important pieces, this launch piston, that's what we're calling it, and this trigger. And you can see they have these little hooks. And so the trigger will release the launch piston, and the springs will propel the piston forward, launching our beanbag out of the barrel. So let's talk about the barrel. We had a couple ideas on how to do this. Our initial idea was to use like a big piece of PVC pipe and basically put the beanbags in there on the face. So we needed a diameter of pipe that was as big as the diagonal of the beanbags, and these were 4-inch beanbags. So we needed a pretty big pipe, which we actually had a hard time finding. We were looking for a 5-inch PVC, but we couldn't. We had trouble finding one. So we thought, well, what's a better way to do this? And we came up to fire the beanbags on edge. So it'd be a much smaller profile. You would just be on edge of the beanbags. They're about, again, 4 inches wide, and the width or the thickness was about 1 inch. So our final decision was that we could use 2 aluminum U-channels, kind of put them next to each other, and you can see the beanbag would fit right in here. And here's a diagram showing kind of the final design that we came up with, and we'll talk about that a little bit more. So we need to determine, okay, how far do we need to pull back these springs to be able to launch our beanbags? How much energy do we need to put into this thing? So we used a handy-dandy internet tool. It was a projectile physics simulation. And you could just enter in, initial velocities, initial angles, and it'll project for you, how far, how long it'll take for this object to reach its destination. So using that, we determined that a pretty good initial velocity for us to reach all possible ranges was around 9.5 meters per second. And that's assuming that the initial height, y0, is about 0.5 meter. So we can use that combined with the average masses of the bean bags to determine how much kinetic energy we need to put into these bean bags. And we did that little calculation here, which is very simple, 1/2 mv squared. We find we need about 5.325 joules into each bean bag to get them up to speed. So we know how much energy we need. We can combine that information with the spring constants of our spring, determine how far we have to draw the spring back. But we need to pick a spring first. Now, when we're doing this, we have to think about a couple of things. First is the beanbags themselves. They're not a solid object, right? So if you just hit it, very fast, very sharply, they'll just deflect. They won't move. So we need to really carry them and bring them up to speed before we launch them. For that reason, we want a much longer draw distance on the spring. So that means we need a pretty low spring constant on this spring. It needs to be pretty loose. So we did some calculations down here. I'm not going to go through all of them for the sake of time, but they're there. And we went through a couple of iterations to decide, well, how far do we really need to have to draw this spring back? And we arrived at the decision that we really need a longer draw length than we initially thought. So our final draw length is about 15 inches, and that meant we need a spring with a constant of about 1.5 inches. And combined with the other systems that we need to build into this thing, we need a barrel length of about 27 inches. And that's what we end up with. You'll see that over there later. Okay, so now I'm going to talk about the trigger. This is the fun part of the system, I think. It's not a control system, but it is very important. All right? If we don't have a way to launch our beanbags, we've got nothing. So let me just walk us through. This is a cross-section of the trigger system. Now this took some working, multiple iterations of pretty much every part you see on this picture. You can see in green on the left here, this is the launch piston that I talked about earlier. It's what carries the beanbag. You can see right here, this is the trigger housing and sear. We're using a servo to actuate this. And we have a spring here which keeps the sear depressed into the barrel. You'll also notice this little box LS here, that's a limit switch. And I'll explain its purpose later. And we have a reel at the back here which is connected to the piston by just a piece of cord, just some cordage. So, let's talk about kind of the procedure of this mechanism. Let's say the software has magically determined that it's time to cock the action. We need to get ready to shoot a beanbag. So the first thing that's going to happen, this servo is going to actuate downward, lifting up the sear, making way. This reel back here is attached to a DC motor, and that's going to start pulling in the cord. So this launch piston is being pulled back, the springs are being extended, and it'll just go. It'll just keep going until eventually, boom, the launch piston hits this limit switch, it says stop, stop moving. At which point, the software knows that it's time to lower this sear, stop moving. So that's what's going to happen. The servo raises up its little arm, the sear lowers into place, and you can see it meets with the piston right there and holds it. And now that the sear is holding back all the force that's being exerted by the springs on this piston, the reel is going to begin turning the other direction, clockwise, to let out slack. So it's letting out a whole bunch of cord at the back of this thing. All ready to fire? The sear is raised up by the servo, all this slack gets picked up, and the beanbag is launched out of the barrel. Voila. So here's a picture of our final assembly. Again, all of these components here, I'm not going to go through them individually, but many, many iterations to get these right.
We have a failure table over there.
Yes, yeah, you'll see on the table, we have many, many failures to show you. Okay, this is a block diagram which shows the electrical design of this system. We have the KL25Z microcontroller controlling everything. We have a 12-volt power supply which is driving our motor driver, which of course in turn drives the gear motor, which pulls back that reel at the back of the device. And we have a trigger servo, which we just discussed in the previous slides, and a limit switch, which again we just discussed. So here's a diagram showing the actual wiring. And again, we have the KL25Z controlling everything, and our driver driving the motor. This is a state diagram which shows the software's basic function. It goes through these 7 states, and these roughly match those diagrams that I was showing you before. I'm not going to go through each one individually right now for the sake of time, but this is generally how it's working using that limit switch, timing, and for right now, button presses. But in the future, the software would use the rest of the gameplay to drive these states changing. This is just a snippet of code showing one of the states. This is the retracting state. So this was that time when the reel is pulling back the springs, pulling back the launch piston. It's waiting for that limit switch to be pressed right here, at which point it will disable the motor, change the pulse width being sent to the servo, which will actuate the servo to a different position. And it'll send that pulse width to the servo. It changes to the next state, resets the timer. Very, very basic state machine software here. There you go, there's a little animation, I forgot. All right. I'm going to turn it over to Quade.
So the first subsystem of mine was the automatic loading mechanism, which is subsystem 2 in this slide. So I just called it a carousel. So basically, the carousel would be loaded by hand, having a full capacity of 20 beanbags. The launcher will make its way to 90 degrees, where it can be loaded properly. Next, the carousel will rotate clockwise, indexing one beanbag into the launcher. So this is what I designed in SolidWorks, and there's a front view, bottom view, and isometric view of the whole thing. And don't worry about the beanbags protruding outside of the walls. They do get squished into the slots. So this is a very simple state diagram of how it works. I basically just told you that it's in an idle state, it waits for a limit switch to be pressed, then it goes into the indexing state. So here's a little picture of how it works. There's a starting position, and I purposely left that spot empty, so it would obviously just fall out anyway. So it indexes one slot, it drops one beam back, and then returns and waits for the next load. This is a little snippet of code in the Arduino Uno, IDE software. So it waits until the limit switch is hit. There's a function to index one slot, a function to stop the motor, and then in a full integrated system, it would then set the launcher state to idle, and then set the carousel state to wait for the next load. So now we had some problems with mounting, so we're going to be the challenges. We faced some difficulty mounting certain parts to the barrel and came up with a list of specifications we had to meet. Firstly, nothing may intrude for the interior surface of the barrel. The 8mm shaft must be mountable and stable enough to handle the forces exerted from the launcher. Also, the launcher must go from 0 to 90 degrees of rotation. So our solution to this was to mount an aluminum dim rail and create mounting clamps that are fixed to the offset yoke, which is coming up soon. So here's a little diagram of the vertical control. As you can see, this is the so the linear actuator just moves up and down and moves the launcher 0 to 90. And there's an offset yoke. And it rotates around that. So now, here's the design of the yoke. So as you can see, the yoke is offset from the center. This is intentionally designed to accommodate the rotation from 0 to 90 degrees with less material than with a standard inline yoke. The rotary mount is housed on the extra bracket on a 10mm shaft. Yeah, the sensor, sorry. The other two inner brackets provide support for the shaft and the bearings. To also give you a scale of how large this yoke is, the inner distance is approximately 8 inches. We also designed this yoke to clamp onto the 8mm shaft using nuts and bolts. So we made a SolidWorks sketch to test and meet the specification of 0 to 90 degrees with the linear actuator having a 4-inch throw. We determined that this actuator worked well through these tests. We had a bunch of different actuators we tried.
Okay, so now I'm going to talk a little bit about that sensor that Quade mentioned earlier. We need to be able to achieve a certain resolution, be able to hit the squares on the board at the distance that we're firing. So again, we want to be able to hit these 1 foot squares, right? So that means we should try to achieve at least a plus or minus half a foot of accuracy to hopefully get inside that 1 foot square. So that translates to about 0.15 meters. So again, we went back to our trusty physics simulation and just fiddled around a little bit and determined, okay, how small of a change in angle is required to minimally hit this 0.15 meters requirement. So we found out about a half a degree of resolution is required to be able to accurately, precisely hit the 1 foot squares at distance. So we have a sensor. Does it meet the requirement? This is a rotary shaft position sensor. It uses the Hall effect to output the absolute position of the shaft by a voltage from 0 to 4.5 volts. And it basically functions like a potentiometer. So the resolution of this, it has 12 to the n bits, 12 bits, excuse me, which is 4,096 steps. And this figures out to about 0.0879 degrees per bit, per step. So this is far above the required resolution we need to hit that 0.5 degree resolution. So this is a diagram showing the assembly for the yoke. This is just a stand-in for the launcher here, just to give you an idea of how big it is. You can see, of course, right here, the linear actuator would be right here. We don't have that in the diagram at this time. But you can see here, these are the clamps that Quaid was discussing earlier that latch onto the rail. Also, the rail is not shown on this diagram at this time. Just to give you an idea of what this thing looks like. So this is a block diagram showing the electrical design of the system. Again, we have the KL25Z controlling everything. We have a motor driver driving our linear actuator. We've got feedback coming from our rotary position sensor going to the KL25Z. Here's a wiring diagram of that exact same system, just showing you how everything's hooked up. We're using a couple of ports. We're measuring from the sensor. So, the vertical control system, this is to give you an idea of what's going on. You can see the red dotted box is indicating the KL25Z microcontroller. We have some controller, a PID controller, assumedly, here in this GC. And of course we have the linear actuator producing an angle in degrees. Our feedback is coming through the Hall effect sensor. It's red through the analog to digital converter on the KL25Z, and that is fed back to produce our error. So, with the software, the user can enter in a reference angle, some sort of target to get to. This gain here, K, is going to convert from angles and degrees to the 4096 count, so that it'll match the units of this A to D converter. So we have to figure out what this gain is. That's what we're going to do on the next slide. So the sensor that we're using has a linear relationship between angle and the voltage. So we can very easily just take 2 points, draw a line between them, and make an equation. So that's what we did. We just use 2 points on there to get a slope, and then just use basic math to get a formula here, so we can convert from some angle that we want to achieve, convert that to a count, which is again from 0 to 4095. Now the software can easily handle that value. So this is just again trying to give you the basic idea of the program is much longer than this. This is just one little screenshot here. So up here we have the feedback coming in from that sensor. And we have here a target, an angled target, which is being converted to the count units from 0 to 4095 in this next line. And then down here, we're calculating errors. This software was set up to do PID control, so there's proportional, integral, and derivative. For our purposes, we don't need integral and derivative, so these gains, Ki and Kd, which are the gains for the integral and derivative, you set those to 0. We don't need those for our purposes. The position, the proportional gain is enough. And so, once the error is calculated, it is sent out of the pulse width modulation port, A2. That goes to the driver. The linear actuator will move to the point that it's been instructed, and the system will hopefully achieve the target we entered in. Wait.
So I did horizontal control and mounting, and the red box denotes the system. So this was my first base design, and this was originally intended for checking the resolution of the encoder, and just a test for it, really. So it has an Arduino Uno and the L29A motor, some gears, laser pointer, and the encoder. So this was my second base design. It has a much bigger platform, which can hold his launcher. It has some shaft support, because I realized that his launcher would wobble a little bit, so I tried to add some more support to it. This is just a continuous, inside the motor box, there's just some gears, a motor, a shaft, simple stuff. So we determined we needed an encoder that could supply us with about 1.2 degrees every 6 inches at 20 feet. So we did some calculations on this current encoder, and it turned out to be just what we needed. This encoder has 2,048 pulses per revolution, and it can count down to 0.175 degrees. This you can see there. We did a test on the encoder and verified that at 24 feet or 5 inches, it rotated the laser 2 inches. So this is the electrical design. 2 motors are controlled by the L298 motor controller, which is powered by a supply of 12 volts. The pins are also hooked up to an Arduino Uno. The encoder utilizes the only 2 interrupt pins on the Arduino, which is important because it needs to be fast to read the A and B channels of the This is just a wiring diagram of the base and the carousel motor and the encoder. So this is the horizontal control system. It's very simple. You input an angle into the software, and it adds that to the summer block, comparing it with the encoder count, and the GC is the Arduino Uno, and the plant is the motor. So this is just a little snippet of the horizontal motor control, which I just showed the output being calculated through all the different gains. And I mean,
Okay, so the last subsystem we're going to talk about is using the Pixie 2 camera. We're short on time here, so I'm going to kind of go at this through light speed here. So the Pixie 2 is a camera with some built-in software. It can track objects, specifically by colors. It can track up to like 7 colors or something. This is just a picture of the Pixie Mom software that comes with it. So you can see it's tracking these blue and red bean bags on the floor. Another thing to point out here is it doesn't always pick them up. It's a little finicky. You know, it takes some tweaking to get it to really work properly and be able to see everything. So some problems we have to deal with when we're using this camera is perspective and distortions. So if the camera's off to the side, it's looking at the game board, it's not a perfect square. Right? It's going to look something like this, more like a trapezoid. Additionally, the lens on the camera has a certain level of fisheye distortion that we have to deal with. And ideally, we would be able to correct completely for both of these. So I'm going to talk about dealing with the perspective. If you imagine that this shaded portion here is our game board, the two lines on the left and the right are going to converge towards some vanishing point. If you've taken an art class, you know all about vanishing points. So let's say we want to figure out the position of this object right here. If we draw a line from the vanishing point through the object through to our baseline, which we're considering the closest line of the board to be undistorted. We're saying that's ideally, that's how big it is. So we can do geometry and basically figure out, what is this length? Well, it'll be whatever this length is right here. And that's the basic idea of the math that I'm doing to correct for the perspective distortion. I'm not going to go through all of it right now for the sake of time. So we'll just move on. So we had to write some software. How is this camera going to work? It's got three basic states, excuse me. It's going to be in the snapshot state, data analysis state, or the print state. Not showing you, there's a little idle state in between the print state and the snapshot state. And that's really for my purposes as the coder. So yeah, during the snapshot state, the camera is going to look at the floor. Gather some data, see what's there. The data analysis state is where we're going to correct for the distortions and the perspective. And of course the print state is where we're going to print that data to the screen, show the user what's going on. Here is a little snip. I wanted to show you guys how I was correcting for the perspective. This is the geometry, this is the data, or the calculations rather, to correct for the perspective in the X direction. And of course, ideally, we're going to correct for all the distortion. Now, that is about it. That was a lot. This is a picture of our final assembly. We didn't completely put everything together. We do have most of it actually put together separately at this point. So, what did we accomplish? We designed the launcher system. We designed the automatic loading system, the vertical and horizontal control of the camera.
But we only successfully implemented the launcher, vertical, and horizontal control. And we were semi-successful when we implemented the camera system and the loading system.
Yeah, I had some issues with the camera system. When I investigated the math to correct for the fisheye lens, it was very, very complex. So at which point I decided, I'll work on a different part of the project, and we'll come back to that later. And similarly, loading, we just ran out of time. There was so much to do. We just ran out of time. Any questions? You know everything. Now you know as much as we do.
Yeah.
Let's do the demo. We actually do have a short. Do you want to do the video first? We have a video to show you the camera functioning. All right, hello. Welcome to our demo video for the Pixie 2 camera portion of our robot battleship project. I'm going to skip as you can see here, we have long. So the camera marks them as coordinates, and we have to take the coordinates, which are limited by the resolution of the camera, and transform that from the view that the camera sees to what is actually on the floor. So we have it set up. I'll place a beanbag on the floor and press the button, and hopefully the camera will detect and report the beanbags on the serial monitor. So first I'm just going to upload the sketch. I'm going to open up the serial monitor once that's done. Okay. So now the camera is waiting. Every time I press this little button up here, the camera will take a snapshot, so to speak. It'll take a look at the game board. So let's press the button. So, if you take a look at the serial monitor, you can see it has detected nothing. All these dashes are signifying empty spaces. So let's see what happens if I go out here and place down a beanbag on the board. Now ideally, the camera will detect that and report it in the correct column and row. So ideally, it'll be in column 1, 2, 3, 4, row 5, column 4. Now, another thing to be aware of is that the reported grid on here is actually rotated 90 degrees from where the camera is looking at. So it would be as if we were standing over there. So let's press the button and see what the camera sees. And it sees nothing. Try again. Sometimes it has trouble detecting objects, so let's just try again. Aha! Okay. So, as you can see, it has detected the beanbag in 1, 2, 3, 4, 5, row 5, and column 4. So that's very good. It's found it. And it even tells us the row and columns, although those numbers aren't exactly accurate at this time. The program is not finished yet. So let's try another one. It can keep track of the objects which were detected in the past, and it should detect another one and report it to the board. So let's press the button. Now, as you can see, it very accurately detects a second object there. And it's accurate to what's on the board. So we can maybe throw another one. Let's put it right here. See if it can see it. And it's a good idea to give it a good 10 seconds to update, to look thoroughly and detect the objects. So push the button. Did it see it? No? Let's try it again. Ah, okay. So it detected at that time. You can see here it is right there. So,
before I demo this, my idea was to input an angle and have it move to that angle. But I think since transitioning it,
something happened when
something
we moved.
happened
Yeah, we don't.
to my program, and it only moves a certain amount.
It does move though.
But it does move. So just a little warning there. So I'm gonna.
We're talking about this guy right here, by the way.
This guy. And as you can see, it's accurately designed.
Is the laser on?
No.
The laser is not on.
You turn the laser
Using it
on.
at all? Oh.
I mean,
Us, just don't worry about
I
it.
think that's fine.
Just move it.
so the first thing you'll see when I upload the sketch, is it will home. The home position is about this corner. So I will upload it and you will see.
It's plugged in, right?
Just takes a minute. So it homes, which is great. So now what I'll do is input an angle, which I'm just going to say 45, and okay, it was working. What the heck? Okay, I'll try a different number. Let's go with 512. 512 is about 90, but
That looked like kind of close.
I'll just
Again,
try.
we had it set up so you could enter in any angle, it would go to it. But
Yes, it
It's
does
moving.
move,
So
and
what if you enter, I mean, the whole point of the laser was to show the resolution, so I don't know what number you just entered, right? You just enter one more, and see it move that one step, or?
I don't know if your video or allows it. I can put in another number.
I mean, something close to that. You have to have the laser on to
Put it.
it's still doing the thing before, right?
Is it still doing that?
It's just moving by like the same amount every time.
Yeah, it's weird.
Yeah.
Okay.
We're not
So
sure what's wrong.
it's like every time I put in a number, it just goes that same amount. Which
Okay.
I'm not exactly sure. But I did have it working before. But
You got a video of it. I keep telling them, take videos of everything. All right.
Okay. Let me just quickly set up for my demonstration here.
yeah, this is the glory of the presentation.
Glory of the presentation.
Yeah.
It's probably gonna land right in that milk carton.
Did you position it to do that?
No.
Okay.
That's about where it lands, though.
All right. Let's hope it hits it.
Okay, so let me just make sure everything's on. All right. So now we're going to demonstrate that this can go to pretty much any angle between 0 and 90. Of course, it needs to go to 90 to load the beanbags in. And it will shoot. It will shoot. We're just going to do manual loading for right now, so I'm just going to put the beanbag in the end there. You can enter any angle in. So let's say I'll demonstrate. You can go to 90. Now we do have this little stop here just to keep it, because of the way it's weighted, it really wants to kick forward, and that would be very bad for our actuator. It would tear itself apart.
And the tolerances on the pit.
Yeah, so just to demonstrate that, I'll bring it back to 45 for us. Hello? 45.
Yours is having problems too.
Wait. Unplug. Yeah, I did. It's canceling.
It is unplugged.
Let's check.
Any wires touching?
Let me just debug this again. Debug again.
The home position is 45.
Yeah.
That's what we're gonna set.
Should. There we go. That was weird. I don't know what happened. So the software is waiting. The fire control software is waiting for me to press button 1. It'll cock the action back. And this is the process that I was describing you before with those pictures. You can step closer and take a look if you want. You can see the servo here is pushing that sear back down. So now this is letting out slack, letting out some cordage. What angle do you guys think we should fire this at? Maybe like 15, 20 degrees? I don't know. We'll do 20. Now I'm going to press this other button and it should fire. Hopefully. So like that. So we can play with this all day. We have had trouble with this trigger mechanism has been especially problematic with either slipping or not being able to release, depending on how big those links are.
I do think it's just the material because it is 3D printed. Plastic.
Yeah. Yeah.
It's not that durable.
It's not exactly a firearm, the components are not metal. It is very definitely a toy.
Let's go to the same angle again. They just
You want to do the same angle?
See if you can hit the same spot.
Okay. It's still at. Okay. Firing. Now, the other thing to point out is that the beanbags they are different masses.
Yeah.
We measured every single beanbag and found a wide spread of different masses. So
just the tiniest
yeah.
bit of weight difference changes the distance. So,
we
shoot the first.
yeah, there you go. That's a good idea.
You think this is from that? Just kind of like that. Let's see if we can hit this piece.
Bring her back up to 45. Okay. Take it down to 20 degrees again. And we'll see if it should go beyond that crate, hopefully. All right. Yeah, about the same spot. So, yeah, that's pretty much it.
Yeah.
So,
Thank you. You showed your other design, so where would that go? Can you take that off the table?
Yeah.
The base here?
So
That would go.
it would go in place of what he's
Yeah.
attached it to.
this shaft right here would mount in to this base.
So that would have been it, but.
And where would the loader go? Go ahead and hold the loader up to where it should be.
So the loader would be about
Yeah.
here. Just above the launcher tip.
All right. So again, the concepts developed here is some of many possibilities. We brainstormed a bunch of them. The teams picked these to explore. And we really don't know what we're doing as far as high school level competition, but we can imagine the two launchers competing against each other. We might have one of the launchers competing against a team of high school students that might come in with slingshots or something that they would design in their STEM class, which we won't have to game. Haven't worked any of those details out. We want to see what the automated systems would look like first and use those as a starting point. So we're happy to see some action like that happening, and we'll see where we go from there. If you guys have any other questions in the audience, the students are all still here. You could ask some questions about their things. If you have some refreshments, we'll be wrapping this up in 15, 20 minutes and sending all this stuff back to the labs. Thank you.
We're giving the fire now. We can fire now.
Oh, okay. Well, let's see this one fire.
All right.
Oh. Got it to work?
Hopefully.
I need a lanyard for that. Thank you.
What's different this time?
I didn't have power going to the pressure sensor.
That'll do it. Yeah.
Is it doing something?
Went right in.
There you go.
Hey. All right. Is it on?
I just need him to load one in.
What pressure was that?
That was 14 psi.
14? Yep. Try a little higher or is it?
A little higher. that one loaded in?
Tower. Back to that.
The same pressure?
That was 1 psi higher.
Do you go a little higher? No. Launch it as far as you can. Max distance.
20 pounds.
It's set to a certain pressure. That was 16 psi.
You said 22 in your bag?
Yeah. Well, 20. Hold on.
Isn't it at 100?
I'll make it 20. Hold on. Supposed to be 20, yeah.
Yeah, so the big difference between the two is that one uses angle to determine distance with a constant spring tensioning, and this uses pressure in the cylinder to determine distance with a constant angle.
Yep.
All right, again, thank you guys for demonstrating. Thank you, audience, for coming. We appreciate all you being out here this afternoon, and if you have any questions, just ask them. Maybe you can all come back next year. All right, thank you.
Before. That's yours.
This is what I'm talking about. Sometimes it doesn't. Let's try it again. What? Wait. I actually want to fix
Ha ha ha.